Now, some strong bases are not readily soluble. They are sparingly soluble or slightly soluble. So, some examples of these, there are others. Examples of these are iron 2 hydroxide and magnesium hydroxide. So, when we look at these, they are usually in the solid form, and we use this equilibrium. If I type it, you'll see it look like this, arrows going in both directions. If I write it, you'll see it like this, half arrows in each direction. And this gives us iron 2 plus, which is aqueous, and 2 hydroxides. So the crazy thing here that's confusing to students in Chem 111 is that we have the solid and it's not dissolving completely. It's not breaking down and completely dissolving, but what does dissolve is breaking into its ions. So even though it doesn't dissolve very well, it does ionize completely. So you only see a very small amount of these. Okay, same thing with magnesium hydroxide. Magnesium hydroxide is not soluble, but what does dissolve breaks completely into magnesium ions and hydroxide ions. So when you think about this idea of not dissolving very well but still breaking apart, then you get a different idea of what's going on in that solution. This is kind of why, like, think about Kentucky. They have really great horses in Kentucky, right? You don't know this? They have some really great horses in Kentucky. They have good chicken. You don't eat the horses in Kentucky, you watch them run. So, in Kentucky, why do they have such good horses? They are bred better, but they breed horses all over the United States, and they send horse stuff all over the United States to breed not in person, right? So it's not really about the breeding. Do you know what it is in Kentucky that makes for great horses? It is the water. It's not the chicken. They don't feed horses chicken in Kentucky. No KFC for the horses. So it comes from the water which gets into the grass which the horses eat. So in Kentucky, Kentucky has a lot of limestone deposits, which is calcium carbonate. And it is not very soluble. But the groundwater eats away at that calcium carbonate, and it ends up with a lot of calcium ions in the water. So the calcium ions are in the water, the calcium ions get into the plants get into the horses, and they have high calcium diets, so they develop really strong bones. And strong bones are necessary if you're going to run really fast and win the Derby or the Preakness or the Belmont, the Triple Crown winner, right? So that's what makes the horses better in Kentucky. They tried to ship the bluegrass seed around, but if it's not grown in the same environment with that same calcium-rich water, they don't get the same results. Now, of course, it depends who your daddy is, too. I mean, if Secretariat's your daddy, you have a better chance of being a good racehorse than if your daddy's Tony the Pony or something. But the whole, it's true. It's true. I mean, it's really a big deal having that groundwater in there. Okay, so some acids and bases are strong. We just looked at the list of strong acids and we looked at the definitions for strong bases. Now, some acids and bases are weak. So when we write ionic equations with weak electrolytes, weak acids or weak bases, we show them in the molecular form. So ionic equations for weak electrolytes, we show them in the molecular form. That's because if you look in the beaker with your molecule seeing eye, you mostly see the molecule, only a very small part is broken apart. So, all of the acids that were not on the previous list are weak acids. And we can think about this, if we think of it in sort of the pop bead demonstration. If we look at that hydrochloric acid, we said hydrochloric acid looks like this. We're going to use red for hydrogen and green for the chloride in this case. It looks like this. It's all broken apart. But if I have hydrofluoric acid, which is a weak acid, and I look in the beaker, what I'm going to see is mostly hydrofluoric acid all hooked together, because only a very, very small amount of it, about 1 to 2%, breaks apart. So you might see something that looks more like this, where it's mostly molecules, but with a couple of ionized units, 1 to 2%. And over here, the HCl, everything is broken apart. So it really gives you a different sort of a result because it is a weak acid. It's in the molecular form. Now, weak bases are defined as bases that don't contain the hydroxide ion. They still produce hydroxide ions in water, but they do that by reacting with the water. So we have a weak base, and some examples of weak molecular bases are ammonia and hydrazine. Ammonia is the one we'll work with the most in this semester. And these can actually react with water to produce a hydroxide ion by taking one of the protons off of water. So weak electrolytes break into ions in an equilibrium reaction. So let's look at carbonic acid. Now I have it written here with water, and I want to write it without the water to start. So carbonic acid, we know this because it's the acid in the Diet Coke, what you drink, right? Carbonated beverages. This breaks apart, and it gives us a hydrogen ion plus a hydrogen carbonate ion. These are now both dissolved in water. And because it's in equilibrium, if you look in there with your molecule CNI, you see lots of carbonic acid, you see a little bit of hydrogen, and you see a little bit of hydrogen carbonate. But now what happens, well, and then the hydrogen carbonate can break apart in another equilibrium, give us a proton and the carbonate ion. So you see very little carbonate and very little hydrogen carbonate and hydrogen. So that's the simplest way. But you'll notice the way I had this typed up in the packet, I have carbonic acid reacting with water. What happens when you put acids in water? We produce protons, hydrogen ions, and that's how I represented it in the strong acid. But a hydrogen ion is just a proton. A hydrogen atom has one proton and one electron. And it wants to be like helium, the noble gas. It wants to get another electron. But in this case, the hydrogen lost its electron, and so now it's just kind of hanging out by itself. It's just a proton, and it's hanging out in solution like, man, I really wanted to be like the noble gases, and now I have no electrons instead of getting two. So when you have water in the vicinity, you remember from your introductory chemistry, water has this bent sort of shape, and there are two lone pair of electrons on that oxygen. So these react, and they make this species. Here's your water with the lone pair. One of those lone pair is now bonded to the third hydrogen, and we make this thing. This is called the hydronium ion. So the hydronium ion, H3O+, is actually a better representation of H plus AQ. If you looked in the beaker with your molecule CNI, you wouldn't see loose protons. You'd really see hydroniums. So we will often see acids written reacting with water to make the hydronium ion, which is aqueous, plus the hydrogen carbonate ion, aqueous. And then we could write the hydrogen carbonate reacts again with water to make another hydronium ion plus the carbonate ion. So don't let that throw you if you see hydronium written down in some of the textbooks. I tend to not write the hydronium ion just out of laziness because it's easier to write H plus than H3O plus. So now let's look at nitrous acid. Nitrous acid reacts with water. We get that hydronium ion again, H3O plus and H plus are the same thing, plus the nitrite ion, NO2 minus aqueous.